Okay, welcome to the optimal sampling calculation example. So I guess I need to get this going. There we go. Optimal sampling. So this is what this example is all about. Try to explain it a little bit more with some numbers so that you guys can follow along. All right, so this little table is what I have gone out and calculated. So for example, here I have calculated I've gone through my data set, I've gone along my profile, and along my profile that I have selected in my data, it's going every 10 centimeters. So every 10 centimeters I can see these are height differences all the way along. So I'm looking at 6 different points and I identify every 10 centimeters what are those 6 points and what's the difference in height. Then I do it again at 20 centimeters and I use 6 different points and I go along those. And then I do 30 centimeters and then 40 centimeters and 50 centimeters and 60 centimeters. So these are individual points. They're control points. So if you can imagine, I've got my profile like this. And I have a point here, I have a point here, I have lots and lots of points that are along. Now ideally you have a lot of data, right? Because it's the only way you can do this. So we have lots and lots of points along here. Let's say they're every 5 centimeters. So if I wanted to do, for example, this 10 centimeters, then I would select a point here, 2, 3, 4, 5, 6. So now I'm trying to calculate what it would be along this line and the difference in height compared to my model. So I'm going to use like a select model. And so, for example, if I had something that kind of went like this through it, that's just an example. But what I'm doing is trying to calculate these differences. So here's my model point, and here each of these points are. Okay. So that's what the sampling, these numbers are from. So I have my unmodeled point and then my modeled point, and then what's the best sampling rate to be able to get it to its correct location. So that's what those are. Now, if I were to do this again and I were to do every 20 centimeters, then it would jump. So I would skip, like for example, the one in the middle there, and I would go even further, right? So I keep along this profile. When you do sampling, you always want to create a profile of the data that you have so that you can optimize from your model and reduce down the amount of memory space. So what do I do next? So my first procedure that I need to worry about is to figure out the average RMSE for each of these different sampling rates. So to figure out my RMSE, I use an equation that is the square root of my change in height squared, and I divide that by the number of values that I'm using. Now, some mathematicians will argue and say, hey, no, you need to minus 1. In this class, we're just going to use n for our value. So when I go through and I calculate, I find that my 0.1, the average is 0.0896, and then 2 is 0.2000, 0.3 is 0.2131, and 4 0.2708, and 5 is 0.2762, and 6 is 0.2982. So now that I have my average RMSE for each of these sampling rates of my data, now I can plot it. So I'm going to put it on a little graph. Along here is my RMSE value, and then along the bottom is my sampling rate. So at my first one here, it's 0.1. My RMSE value is 0.8, so if I say this is like 0.1, then it's just going to be just below. And then my next one is 0.2, 0.3, 0.4, 0.5, 0.6. So at 0.2, it's at 0.2, so 0.2 jumps up to there. And then at 0.3, it's just above the 0.2 value. It kind of flattens out a little bit. And then 0.4 jumps up. And then these ones flatten off again. So we end up with something that looks like this. Okay. Now the question is, if I were to have a optimal sampling location of 0.25, so that means I'm now going to look on this side of the graph. I'm going to say, okay, 0.25 is about halfway in between 0.3. So this is 0.25. This is my client's expectation, right? I want an accuracy of 0.25. So I find that on my RMSE axis, and then this is now my sigma int. Then I draw some dots across my graph, and I find that it's in between here, and we're trying to figure out where does it fall in between these two values. So that is what we're calculating. So all we've done is just found these RMSE values by taking the sum of each value squared, these change of height squared, divided by n, got my values, and then I plot them, and then I'm given this, so this is given. My client says I need it at 25 centimeters, so here we are. So now my next step is to try to figure out where is this. So those are those formulas that I gave you when we were doing the lecture. So my first one is delta. I got to figure out delta, and this one is my sigma int minus my RMSE function at k minus 1 divided by my RMSE at k minus RMSE at k minus 1. So now you're like, well, what's k? So we can actually look at the x-axis for this. So this one is k equals 1, because that's my first sampling rate. Here, k is equal to 2. Next one is k equals to 3, and then 4, and then 5, and then 6. So that's what the k is. So it's just counting each of these. It's literally just a counter. So k equals 1, k equals 2, k equals 3. No matter what these values are down here, that's what k is going to equal to. So we're going to put that into our formula. So we have sigma int, which is 0.25. And we're going to minus the RMSE at k minus 1. So k is always going to be the top one. So we know that k is equal to 4. That's the top one. So I have to go down to k equals to 3. I need to find out what that value was. So k equals to 3 is 0.2131. So this is k RMSE at k minus 1. Okay, so that's what that stands for. So I have 0.25 minus 0.2131. And then I need to look at my k value, my RMSE at k, which is at the 0.4, so it's this one. And so my value is right here, so I go 0.2708 minus 0.2131. And when I do the math through this one, I get 0.638744. Now we are not at the end of this calculation yet, right? Because all we did was calculate delta. So now we need to actually put it into like the actual value, right? So we need to figure out what is my optimal sampling distance. So when I'm doing the calculation for the optimal sampling distance, I am looking for the place on the x-axis that this is going to work at. So here I have my sampling rates. So what is the value here? That is what this last part is calculating. So my sigma d opt, to calculate that, we have my k minus 1, and then plus my delta value that I just calculated, and then we multiply that by delta d. Now, what is delta d? Delta d is the difference between each of these steps. This particular operation only works if you have regular steps in between your distance. So we know that delta d is equal to 0.1 because it's going up by 0.1. Now, if it went to like 0.1 and then the next one was 0.15, then my delta d would be 0.05, just 10, 0.05. If it was going up by 25, like 0.25, then this would be 0.25, right? So that's what that value is. So if we put that in, we now have 4 minus 1 plus my delta d value, which is 0.638744, multiplied by 0.1. And we get a value of 0.364. Which is going in the millimeters. So these are all in meters. So does that make sense? So if my delta d opt is at 0.364, so we go back to my graph. I find my required accuracy, which is 0.25. I go across that graph and I go down, and it is in between 0.3 and 0.4, and it is a little bit closer to 0.4 than it is to 0.3. So this makes sense. So that is my answer. So that's how you do optimal sampling with this style. Now the other option is to look at the roughness factor. So we're talking about roughness factor. This doesn't quite work with this particular data set, so I'm going to close this one down. I will do roughness factor as a separate example in another video, but this one is probably the most complicated one, so you may have to watch it a couple times.